The space between the Earth and the Moon is rapidly becoming the next operational frontier for human spaceflight. To support this architecture, agencies are using Lagrange points, specifically L1 and L2, as logistical staging hubs for deep space missions. But navigating vehicles between these points takes immense computational power. Right now, spacecraft are effectively tethered to Earth, relying on giant ground station antennas to beam calculations from servers back and forth. That umbilical cord has a severe flaw. When a spacecraft passes behind the Moon, it experiences a total communication blackout. Combined with standard transmission delays across space, the vehicle often finds itself flying blind for critical stretches of the journey. Without continuous contact, any unexpected push from a solar flare or a lunar gravity anomaly can knock a logistics craft off course, leaving it entirely exposed to orbital drift. These missions typically run on high-efficiency, low-thrust electric engines, like these ion thrusters. To move a spacecraft, they have to provide a continuous thrust for days or even weeks at a time. Executing a long burn in cislunar space means dealing with the circular, restricted three-body problem. You have both the Earth and the Moon constantly pulling on the moving spacecraft, creating a chaotic, non-linear tug-of-war. Traditional navigation software relies on gradient-based optimization to calculate a path through this environment. But in the three-body system, those solvers routinely get trapped in local gravitational anomalies, which can easily plot a course that sends the spacecraft crashing into the lunar surface. Relying on standard math solvers is simply too risky for a spacecraft trying to guide itself. They need the heavy lifting of a ground-based supercomputer to spot and avoid those mathematical traps. Researchers are solving this by moving the entire guidance system directly on board the spacecraft, using low-power edge processors that consume less than 5 watts. That is roughly the same thermal footprint as a mobile phone chip. They execute this using an architecture called SIMD. Instead of calculating one trajectory at a time, it evaluates multiple paths concurrently. Using a structure of arrays memory model, the system packs flight data into 128-bit registers, processing 4 independent trajectories in the exact same cycle. This setup entirely removes the need for complex calculus and fragile gradient solvers. The system just brute forces a massive grid search of every possible route at once. By structuring memory this way, a tiny embedded chip can instantly output the raw computational volume you would normally expect from a massive ground facility. This 3D plot shows this in flight. The spacecraft departs the first Lagrange point along the pink path, arriving at a trajectory correction maneuver node. Right at this diamond, the onboard computer uses parallel speed to test thousands of potential flight paths simultaneously. The processor evaluates 20,000 candidate trajectories in 323 milliseconds. That is over 123 million integration steps per second, running entirely on a single mobile core. This chart maps the result of that calculation. By scanning a full 360 degrees of possible steering angles, the system definitively locates the exact optimal thrust angle, hitting a global minimum at 208.36 degrees. By calculating every mistake millions of times faster than they can happen in reality, brute force parallel computing safely navigates the chaos of the Earth-Moon system. Looking at this 2D trajectory plot, we can see the spacecraft perfectly hits the target capture zone, intersecting what physicists call the Poincare surface of section at the lunar plane. The terminal miss distance lands at just under 97 kilometers from the absolute center of the target. Modern lunar insertion margins require accuracy within 50 to 120 kilometers, meaning the SIMD framework hits the window exactly. It achieves this precision while maintaining strict fuel economy. The entire maneuver requires a delta-V expenditure of only 164.5 meters per second, keeping it squarely in line with the required budgets for low-thrust space missions. These metrics prove a small onboard chip can eliminate dangerous gravitational capture traps while preserving the propellant needed to actually complete the mission. Because this massive computation takes only a fraction of a second, the spacecraft gains a capability known as continuous receding horizon control. It can recalculate its entire journey to the Moon from scratch, at any moment mid-flight. If a burst of solar radiation or a dense lunar mass anomaly pushes the craft slightly off course, the system doesn't drift. It instantly re-evaluates the environment and adjusts the thrusters to absorb the disturbance. In the past, you would have to wait for the deep space network to track the error, wait for ground crews to calculate a fix, and wait for the transmission to return, hoping the vehicle hadn't spiraled into a crash in the meantime. By generating supercomputer throughput on a mobile chip, SIMD edge computing cuts that tether to Earth. It turns cislunar logistics vehicles and deep space CubeSats from remote-controlled drones into fully autonomous, self-correcting robots.